Okay, this lesson is another one that's pretty quick and it still has to do with limits. We're going to talk about how to estimate limits from tables here. So that's a fun visual pun. It's a table, but not that kind of table, numerical tables. So I'm going to guess the value of the limit of x minus 1 over x squared minus 1 as x approaches 1. So we're going to talk about how to use a table of values. And this is something I kind of went over in the last example of 1.3. But we're going to use our calculator to do this. So what I want to do is throw my limiting function into the calculator. So let me pull up my calculator. Move my image. There we go. So we're going to y equals, and you want to use parentheses here, so it's going to be x minus 1 over x squared minus 1. Nope, I need to open parentheses. All right. So I'm just deleting out anything that's in there, and we just want to remind ourselves what the limiting value is that we're approaching. So we're approaching 1. And it's also very important that you recognize that, remember, for the overall limit to exist, the limit as x approaches 1 from the left of this function has to equal the limit as x approaches 1 from the right of this function. So when we're using our calculator to try and estimate it, it's important that you approach from both sides of 1, from the left and the right. So values to the left of 1 that are close to 1 are things like 0.9, 0.99, 0.999, and so on. And values to the right of 1 that are close to 1 are like 1.1, 1.01, 1.001. You can start with larger numbers if you want, but what you need to remember is what we really only care about is what's going on as we get infinitely close to 1 from both sides. All right, so let's do this. So we'll start on the left of 1, 0.9, 0.99, 0.999, and it looks to me like it's approaching 0.5. And if I go from the other side, 1.1, 1.01, same deal. It does seem to be approaching 0.5, right? So based on that, we're just going to make our educated guess and say that the limit of x minus 1 over x squared minus 1 as x approaches 1 equals 0.5. That's it. So pretty similar to how we were estimating them using graphs. It's just now we're using tables of values. We'll try the same thing here. All right, for the second one, we have another kind of ugly function. But we're going to approach it the same way, and it's still important to remember the same thing. So I'm going to reference this as f of x. F of t. So it's just important to always remember if you're trying to evaluate the overall limit and you're trying to estimate it by using a table, you need to check from both sides of your limiting value. So I need to check what's going on with f of t as t approaches 0 from the left, and what's going on as t approaches 0 from the right, and I need to make sure that those seem to be equal when I put it in a table of values. So went ahead and plugged my function into y1. Okay, you want to make sure your table is set to, the independent variable is set to ask. If you have stuff in there already, you can just delete it out. And then remember what your limiting value is. So I'm approaching 0. So if I want to approach from the left of 0, numbers that are to the left of 0 are negative. So I want to choose negative values that are very close to 0, like negative 0.1, negative 0.01, negative 0.001, And it does look like we're approaching 0.16 repeating, right? Let's try one more. Negative point. Sorry, I think I did too many and my calculator got round off error. All right, so let's see if it does the same thing from the other side. So if I approach 0 from the positive, like, 0.1, 0.01, 0.001, 0.0001. Yeah, it does seem to approach 0.16 repeating, which is actually 1/6. But again, it is important that you check on both sides of that, and so I would say that this equals 0.16 repeating, which is 1/6. All right. So we are going to get to ones that are a little bit trickier. So this one we want to look at what's going on with x cubed plus cosine 5x over 10,000 as x approaches 0. This one's not especially difficult, and you can just do it in your calculator the same way. Make sure that you are approaching 0 from both sides. So if I call this f of x, I want to look at what's going on with f of x. So to the left of 0 are numbers like negative 0.1, negative 0.01, negative 0.001. And then also make sure you approach 0 from the right. So again, numbers close to 0 that are to the right are positive, 0.01, 0.001, and so on. But I also want you to be able to have a general intuition for what's going to be happening. So what do we know about cosine? Well, we know that it oscillates between negative and positive 1, right? Up here we have positive 1, down here we have negative 1. So whatever this number is, as we let x get closer and closer to 0, it's going to be a really small fraction because at its biggest, cosine can output a value of 1. So at its biggest, that's going to be 1/10,000th. So it's also important to know that cosine of 0 is 0. So as you let x approach 0, your value for cosine is going to go towards 0. So this numerator is going to be consistently approaching 0. X cubed, as you approach 0, gets smaller and smaller. So this is going to approach 0. So you're going to expect overall that this is going to approach 0 plus 0, which is 0. So I want you to start developing an intuition for what you think these limits are going to come out to before you actually start throwing them in your calculator. But we can just verify that right now. So again, I plugged that function into my calculator. I'm going to go to my table. I'll start on the left. So if we plug in values to the left, like -1, get closer, whoa, sorry, go to -0.5, -0.4, -0.3, -0.2, -0.1, 0.01. And that's scientific notation. Anytime you see a negative exponent, it's just a very small number. Let's come in from the other side. 1, 0.5, 0.4, 0.3, 0.2, 0.1, and it does exactly what we thought. It begins to approach 0 from both sides. So we're going to say overall that this limit is 0. All right, now this is a weird one. And I want to show you why. So let's pull up the calculator again. And let's go to y equals, and let's enter that sine pi over x into our calculator. Let's go to our table. I'm just going to delete all this out. And what if I use the same general tactic that I used, which is I'm approaching 0. So let's get closer to 0.0 or closer to 0 by using like -0.1, -0.01, -0.001. Let's see what would happen here. So if I do -0.1, -0.01, -0.001, -0.0001, You might go, oh, maybe that's my calculator rounding off. Nope, it thinks it's actually 0. Huh. All right, what if I get close to 0 from the other side? So 0.1, 0.01, 0.001, 0.00001. They're all 0, so we might be tempted to say that our limit is 0. This is where it becomes important that you try and verify things in other ways, okay? Here's the reason. It's because I'm specifically using factors of 1, 0.1, so tenths, hundredths, thousandths, and so on. So let's think about this. If I have sine pi over x, and I choose to plug in 0.1 for x, that's sine pi over 0.1. That's sine pi over 1/10. That's sine of 10 pi. Any even number multiple of sine comes out to 0, because any even multiple number of pi is a coterminal angle with 0 and 2 pi and 4 pi and 6 pi and 8 pi and 10 pi on the unit circle, and so on. So any value there, sine of that angle is going to be 0. Whoops. So we want to be really careful, because each time I was doing this, I was actually choosing a multiple of 10 pi. So like when I plugged in 0.01, well, 0.01 is 1/100th, so that's sine of pi over 1/100th. That's sine of 100 pi, which is still a coterminal angle with all of these, so you're still going to get 0. So this becomes really obvious when we look at the graph of what's going on here, but I want to show you in the calculator. So let's say I don't just use these factors of 10, these multiples of 10. What if I get closer by using kind of more random numbers? So I go like, okay, so negative 0.1 gave me 0, but what about like negative 0.03? Oh, well, like negative 0.004. Okay, 0. Negative 0.004125. Huh. Now I'm actually getting outputs, even though I'm getting closer and closer to 0. Negative 0.000013256 Oh, now I'm negative. Okay, so now we don't seem to be approaching anything in particular, even though I'm putting in random numbers that are closer and closer to 0. And let's see why. This is kind of an interesting function. All right, I'm going to use GeoGebra just because it's a little bit more robust. But if we look at sine pi over x, we end up with this. And what's going on here is as you approach 0, this sine function actually begins to oscillate faster and faster. Okay, so my recorder acted up there, but hopefully what you saw was that as in that graph, as the function got closer and closer to 0, sine kind of oscillated more and more quickly. And so as we get closer on either side, it actually begins to oscillate infinitely fast and never approaches a single point from the right and the left of 0. So this is a kind of a special case where we would say the limit of sine pi over x as x approaches 0 is undefined, or does not exist. So DNE stands for does not exist. UND stands for undefined. All right, so here's a good kind of AP type example where you're given a table of values and you have to use what you're given to make sort of a decision about what's going on. So the table gives values of a function f at selected values of x. Which of the following conclusions is supported by the data in the table? And so all of these have a limiting value of 3 in the answer. So what we want to see is, can we determine anything as we approach 3? Well, as we approach 3 from the left, notice that my y values seem to be approaching larger and larger negative values. -8, -80, -800, -8,000. And as we approach 3 from the right, my y values seem to be approaching larger and larger y values. So 880, 800, 8,000. So none of these actually have to be true because they don't give us enough information to draw the conclusions, but which one is supported by this data in the table? Well, remember, for an overall limit to exist, the limit on either side of your limiting value has to be approaching the same thing. In this case, to the left of the limiting value, our y values are getting really negative, and to the right, we're getting really positive. So I wouldn't expect that they are approaching necessarily the same thing. So I would say probably the best supported case is that the overall limit does not exist. All right, here's a similar example. See if you can come up with some support for one of these answers, and we'll talk about it in class.